On behalf of Space Education and Research Foundation, and on my personal behalf, I am very happy to welcome Dr. Ritesh Kumar Mishra, the speaker for this webinar on the origin and evolution of the solar system. And as you all know, and also the participants for this webinar. This series will have 5 lectures, and 2 lectures already Dr. Ritesh Kumar Mishra has given, and today is the 3rd talk, and the title of the today's talk is Cardinal Questions of the Solar System, and he will give more emphasis to born with a bang or bleed. That is the topic of main discussion today. Before I hand over the mic to Dr. Ritesh Kumar Mishra, I briefly say a few words about him. He had a very excellent academic career, schooling as well as post-graduation and graduation. He did his PhD in Physical Research Laboratory, and also a postdoctoral work at PRL, and after that he has done extremely good work at several premier institutes around the globe, including NASA and in France, Germany, and several other places. He had quite a good collaboration with several of the scientists around working in the field that he is now actively working. With these few words, I now request Dr. Ritesh Kumar Mishra to start his talk, and I, along with all of you, will listen to him. Dr. Ritesh Kumar Mishra, please.
Thank you, Dr. Watts. So in the 3rd talk of this series, we will be slowly getting to the nitty-gritty of the question of the origin and evolution of the solar system. So let's recap what we said in the first 2 talks. In the first talk, we talked about our solar system, how it looks like, what it is architecture, and what kinds of exoplanets are we observing around the world. So by observing the architecture of our solar system, we found out that probably we are the only planet that hosts life. And so to be able to understand our position on this habitable planet, the larger question of the origin of a planetary system around a star was raised, and therefore we wanted to know how did our own solar system originate, such that out of these many stars that we currently see, we are the only one, so far as we know, that hosts life. In the next talk, we talked about how does this matter, or the stars and galaxies, come about? How do they form? So it starts from a gut era, and then first baryons are created, and then nuclides happen, and then atoms get together, and then these atoms go into the stars, and the stars eventually form galaxies. And so that's how we are 4.56 billion years down the line, while the universe started at about 13.6 billion years ago. In the same talk, we also talked about the chronology of the solar system, and we saw that typically a star is born out of a collapse of a molecular cloud, and then depending upon where the cloud collapses, the material that it incorporates, therefore solids and ice, form out of the protoplanetary disk once the star is born, because of the thermal gradient that is created by the radiation emanating from the star, and the subsequent condensation that takes place farther and farther outward from the sun. These solids then get accreted into planets if if they accrete too quickly and are massive in size, then they undergo differentiation and we get iron meteorites or iron kind of a planet with a composition that of an iron or iron nickel, and that's how, and therefore we saw that as we exist today. So we will be talking about a few very important questions about the origin and solar system, which are very, very critical. One of those questions would be addressed today, and that question is about whether the collapse of our molecular cloud was a natural one or was it triggered by the death or by the winds of a nearby star. So so in a molecular cloud, if in a molecular cloud, if simultaneous collapse of several cores takes place, then stars of different masses would be born. A more massive star would would burn out more quickly, and therefore by the time the less massive star like our sun is born, the more massive stars, let's say of about mass 8 or 10, would be in its last phase of the star, and therefore it would go to a supernova stage, and it would generate a shock. That bang, that supernova shock would force the gas and the cloud in our solar system, leading to a hastened collapse of the molecular cloud, or what we call as a triggered collapse scenario. So these have a large implications because if the collapse of a molecular cloud is triggered, then most of the events are hastened by several million years, because of which the major heat source, which is 26 aluminum, will come to that in a short while, will be far greater in amount, leading to far more dynamical evolution of these planets that we see, which means the internal heat that will be captured by these planets will be far too high compared to a natural collapse, and therefore the geological evolution of all these planets would be very, very different. So one of the main reasons why we exist on this earth is our earth is a living planet, which means cycles are going on. So the cycles are continuing. So matter and energy is being circulated in several cycles, carbon, nitrogen, and all that, which happens because of the geological activity of the sun. So plates are going down, and therefore they're sinking all the material downwards, and then it's being brought back again by volcanoes and all that. So if that stops, then the circulation stops, and therefore and then that leads to difficulties in sustaining life as we currently know it. So we'll be handling that question. So in this slide, what we see is the current architecture of the solar system. We can see that we have an Earth-like planet in the habitable zone on which we are residing, and by studying the meteorites, which is shown in the lower panel, at a scale of about 50 and 100 microns, we can make inferences about the origin of solar system, and thereby constrain how our own specifically solar system was born. So during last 3-4 decades, a lot of progress has been made in almost all areas of planetary sciences. In fact, in all areas of science and humanities. In the area of planetary sciences also, because of observational and theoretical work, a lot of progress in each of these subfields have been made. So we know quite a lot, but still there are gaps, which we'll see in the following slide. So this slide beautifully summarizes what we currently know. So this is a log plot of the size of the objects on the y-axis versus the time scale on the x-axis. So from this plot, we can see that a micron size dust particle condensing in our solar system of the size of a few microns by condenses out of the solar system, then these gets agglomerated, and then some of them melt because of the heat in the disk, and they form different kinds of different objects called CAIs and chondrules. These objects again accrete to form smaller bodies called planetesimals, and then these planetesimals, by impacts and oligarchic growth and runaway growth, leads to formation of planets like Mars in a very short period of time. So there is a growth of an order of about 12 orders of a magnitude in a few million years. So what happens is, from these micron-sized particles to planet-sized objects are formed in a few 2 to 5 million years, and then most of these objects more or less evolve in the same way for next 5 billion years to 10 billion years as the life of the star is. So most of the grand architecture of our solar system was established in the first few million years, and since then for next 4.5 billion years we have been more or less same physical state. When I say physical state, I do not mean that there has not been change of oxygen, rivers, water, plants and vegetation, but these are very minuscule changes on the scale of a planet. So there has not been that kind of a change of 6 orders of magnitude, going from a dust submicron size particle to becoming a few thousand kilometers in size. So a sequence of cataclysmic, rapid, highly energetic, large-scale, sequential and often simultaneous sets of events involving condensation, agglomeration, collisional and runaway growth leads to formation of planetesimals to planet in a very short period of a few 10,000 kilo years to a few million years. Then following the formation of these planetesimals, most of the matter has been accreted into these planetesimal sized bodies, and then from that particular time, a few million years past the starting of this or beginning of the solar system, for next 4.5 billion years till now, and for next 4.5 billion years to come, the grand architecture will more or less remain the same. So while a lot of progress has been made in these areas, there are still several first order questions that have not been very precisely addressed, or addressed to the level of accuracy that is required, or to the level that these events, on the time scale at these events occur. For example, can we constrain the absolute and relative timescales of each of these events? So did this solar system form at 4.67.2? When we say 0.2 million years, 0.2 million years, it is still 200,000 years. And 200,000 years is a relatively large scale of time. We will see shortly as to why that 200,000 years. So that accuracy of about a million year is a long time in the realm, or in the scale of the events that we will talk of. These events take place for a few 10,000 years or a few thousand years. So on the scale of few thousand years, 100,000 years is a 100 orders of magnitude larger in time. So we want to constrain those events to the time scale that these events are taking place, which somehow we have not been able to constrain. So we want to know, when did the last injection of material to our solar system took place? Did that happen right before this formation of solar system, or the material continued to be added before and after the formation of solar system? When these objects were forming, were these objects forming in different time at different scales, and was it forming from a homogeneous environment, or they formed in an inhomogeneous environment, and therefore the heterogeneity in the structure, in the chemical composition exists? In what kind of environment were these events taking place? What were the kind of temperature, oxidation, radiation fields in the surrounding environment, because of which we see the large amount of diversity in the terrestrial and and the gaseous giants. The kinds of scales at which these events were taking place, were these taking place at a few thousand kilometers, or they were taking place at a scale of a astronomical unit scale? Did they happen continuously one after the other, or did they follow a particular pattern of events, one sequentially following the other, and the condition repeating over and over again to give several sets of similar kinds of objects with a slightly different composition or a diversity? So these all will become very, very crucial in understanding the diversity and the establishing the architecture that we currently see in the planetary system. So how do we do it? We do it by using radionuclides. Inside meteorites, we find evidences of several short-lived, now extinct radionuclides. Short-lived because they lived for a short period of time. Now extinct because their half-life is so short that they are extinct during the first few million years. Therefore, they are extinct today, and 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 because they are radionuclides, they can be a very useful tracer of the time and events at which each of these events was happening. So in this slide, what we see is about more than a dozen such short-lived radionuclides are currently known. In this slide, those are shown. On the extreme left, we see the short-lived radionuclide. Then we see its characteristics half-life, the dot product in which it decays, and what is the inferred abundance at the time of the formation of the solar system. So because these are radionuclides, they will continue to decay, and therefore at different time since the beginning of the solar system, their numbers would be different. We need to know what was the initial number so as to be able to tag the events that sequentially that happened after the formation of the solar system. So for example, 26 aluminum has got half-life of 0.72 million years. It decays to 26 magnesium, and the initial solar system initial abundance of 26 aluminum normalized with respect to the stable isotope, which is 27 aluminum, is 5.23 times 10 to the power minus 5. So for every 1 million atom of the stable isotope of 27 aluminum during the time of the birth of the solar system, there was just 0.2 half atom of 26 aluminum. So similarly, the list goes on, and since these are radionuclides, each of these nuclides are created in a specific environment. They have a particular pattern of, they have a particular amount of neutrons and protons, and therefore they are created they could be created by specific processes, and therefore they are also the tracers of the source from which they come from. So for example, some of those, so each of the source which could possibly make these, some of the major source which could possibly make these have been shown over here. So these could be made in supernova, they could be made in an asymptotic giant run star, or they could come from Wolf-Rayet star, or they could be formed by spallation reactions by the irradiation in the early solar system. So there are few nuclides like 41 calcium, 26 aluminum, 53 manganese, which could be created by all of these processes together. But there are a few nuclides which are distinct tracers of a particular source. For example, 60Rn. 60Rn is only created by stellar sources. 60Rn is too rich in neutrons, and therefore it requires a large amount of energy or a push to push 4 extra neutrons into 56Rn to make the radioactive 60Rn, which is that kind of energy exists only inside massive stars, or at the explosion of supernova, and therefore this nuclide is created specifically by the stellar sources. Similarly, about these nuclides could also be created by supernova and asymptotic giant branch. So if we can find these radionuclides and determine their abundance in the solar system, we can reverse engineer to say what source contributed these nuclides, and thereby we would be able to fix the kind of environment in which our solar system was formed. Similarly, there are nuclides like 7 and 10 beryllium, which are hypothesized to be forming only from irradiation. I have shown it between supernova and irradiation. We'll come to this in the last lecture as to why I have shown it between supernova and irradiation. 7 beryllium and 10 beryllium, because of very low binding energy, they are consumed inside the stars at a temperature of about a few million degrees Celsius, and therefore beryllium and boron are not produced by this inside the cores of the star. We'll see how in some specific scenarios they could also be produced by star, and therefore it rightly resides over here between supernova and irradiation. But for most part, 7 beryllium and 10 beryllium is created by spallation reactions, and therefore 7 beryllium and 10 beryllium, some specific smoking gun for nuclides that are produced by spallation reactions, which means that they should have been created by interaction between irradiation from a stellar source with the gas and dust around. So, a brief primer on the radioactive decay. Most of you know that a radionuclidic decay would follow a logarithmic law. So, n numbers of nuclides, n would be number of atoms at a particular point of time would be equal to the number of atoms that it started with, and it would decay with the exponential law. So number of atoms today would be equal n would be equal to n0 times e to the power minus lambda g. So supposingly, so a radioactive nuclide like 26 aluminum that beta decays to 26 magnesium in a half-life of 0.72 million years. If this 26 aluminum was incorporated inside a solid, then the 26 magnesium that we see today would be equal to 26 magnesium that was present initially plus the 26 magnesium that came from the decay of 26 aluminum into that particular object. So this can be converted into a linear equation by dividing both sides by a stable isotope which doesn't have a radiogenic precursor. So therefore, we get a linear equation of type 26 aluminum by 24 magnesium is equal to 26 magnesium by 24 magnesium initial plus this 26 magnesium by 24 magnesium. But this 26 magnesium is coming from 26 aluminum, so we can change this 26 aluminum for the 26 magnesium divided by 24 magnesium and then multiply and divide by 27 aluminum. So we get a linear relationship of this type whereby we can measure 26 magnesium by 24 magnesium in that object, and we can also measure the elemental abundance or the isotopic ratios of aluminum and magnesium in that particular object. If we plot these two, then we'll get a slope. This is an equation of the type y equals to c plus m times of x. So if we analyze a few phases with varying amount of aluminum and magnesium, then we'll obtain a line, the slope of which will give the abundance of 26 aluminum by 27 aluminum at the time of its formation, and the intercept of y-axis will tell you what was the initial composition of 26 magnesium by 24 magnesium at the time of the formation of that particular object. Since these excesses are typically very, very small, therefore they are expressed as the deviations from a given standard in parts per thousand. So this is converted as an excess with respect to a reference in parts per 30,000, and it is called delta. So now, because of the physical process, there could be some physical process which could have obliterated, which could change these ratios. Therefore, to be able to account for this kind of a post or a pre variation in the isotopic ratios, this is a mass fractionation correction is done using a relation something like this, where delta 26 magnesium is equal to 26 magnesium minus beta times of delta 25 magnesium. So if, as I said, if we can plot this versus this, we'll get a line. The slope of this line will give the initial abundance at the time of its formation. The intercept will give you the initial magnesium isotopic composition at the time of the formation. So for an object like a CI shown over here, we can infer that the 26 aluminum by 27 aluminum was 4.77 times 10 to the power minus 5. When this is inferred in terms of time, this is of the order of 30,000 years. So we can constrain those events to a time scale of 30,000 years or to a few thousand years level too, with the advanced level of analytical precision that we currently have. So this kind of a such kinds of measurements allow you to date events recorded in these meteorites to a level of 34,000, about 4.56 billion years ago. So just as to how does this happen inside a meteorite. So let's say we start with a homogeneous solar system where elements and isotopes are homogeneously distributed throughout the solar system. Then, because of a physical or a chemical process like condensation, preferably one mineral would preferably choose a few elements, and therefore there will be a partitioning of that element between that solid and the leftover gas. So, for example, in the process of condensation of in the process of formation of an olivine, magnesium and iron would be preferentially taken compared to aluminum. So olivine would have a more amount of magnesium compared to aluminum than the magnesium aluminum ratio in the surrounding solar cloud. So if that fractionation takes place, then the objects formed would have different amount of 27 aluminum by 27 magnesium, and because they have radiogenic 26 aluminum, with the progress of time, the larger amount of 26 aluminum you will have a larger ingrowth. Similarly, and therefore if you measure these now, you will get a slope where the slope of this line will tell you what was the initial abundance at the time of formation of these objects. Supposingly that event doesn't take place as time t equals to 0 and happens slightly later, then 26 aluminum would have decayed. Some of the 26 aluminum would have decayed into 26 magnesium, and if that fractionation process happens now, then you would obtain a line which has a shallower slope but a higher intercept. So by figuring out these kinds of things, you can say a lot about events and processes in the early solar system, which we will see in the following slides. This is the most crucial part for you to understand, to be able to follow the logic that we are going to discuss subsequently. So, as I said, there are several very, very important questions, and as I said, these events need to be constrained at these kinds of time scales, the relevant time scales at which these events take place, and not at millions and billions years. We need to constrain these time scales to a few thousand years to a few 10,000 years, because that is the time scale at which these events takes place. So there are questions like, did the solar system start with a homogeneous composition? For example, if the triggered collapse happened, then some material would be injected into the solar system, and therefore the injected material would take some time to homogenize. So at what time did this kind of a homogenization take place, or did solid started to form even before the homogenization took place? What was the story? What is the constraint that we can arrive out of it? This has an implication again on forming the architecture that we have. Similarly, then we have a question about whether the collapse of the cloud was triggered or it was natural. If it was triggered, then was it triggered by the death of a star, or was it triggered by the wind of a massive star in close by during its W or O stage? And then similarly, we want to understand how was the sun during its birth. So how active it was, what was it doing, was it rapidly changing its irradiation, and those kinds of things, because again those things would affect the way solids would form, evaporate, and get together. So if there is a very high intensity event, then suddenly the temperature would increase because sun is now emanating more, and therefore all the solids would evaporate, and therefore gas is more closely coupled to the capillary motion, and therefore they would not form solids immediately if that irradiation event doesn't happen. So these things again have an implication for where these planets form, how these planets form, and what kind of composition they will have. So today what we are going to specifically look at is, did our solar system collapse naturally, or the collapse of our solar system was triggered by a nearby source? So to be able to answer that question specifically, we are going to look for the specific nuclide 60Rn that we talked about. But before we talk about that specific nuclide, let me give you a brief glimpse of what do we mean by meteorites, and what kinds of meteorites exist. What we really mean by meteorites. So meteorites are rocks that fall from space and they land on Earth. If the rocks are burnt out completely during the entry, if they are burnt out completely, they are called meteoroids or meteors. Meteorites are those rocks which somehow survive because they are big or large, or because of the angle with which they are entering the Earth. Some portion of it survives to land on the Earth. Now, these could be of all different kinds. These have a broad, there is a very large diversity in the kind of composition that we see in these objects. So they are broadly classified into two types. One are called as chondrites. They are called chondrites because they have what is called as chondrules. We'll see what is a chondrule. And then there are others which are called non-chondrites. These are objects which have seen some kind of a melting and reformation. So they do not have those. They mostly do not have chondrules. The non-chondrites can be further divided into primitive and differentiated. Differentiated ones are those which have melted completely, and therefore there has been separation of silicate and iron. Silicate and iron, and then there are some in which both could be found. So the differentiateds are categorized into irons, which are completely iron with with limited amount of silicate inclusions. Then there are stony irons, which are a combination of both, and then there are achondrites, which are primarily silicate but have a significant portion of iron also in them. We also have some meteorites coming from Mars and Moon, and the meteorites from Mars and Moon are categorized as Martian meteorites. They are categorized into Shergotite, Nacolite, Cassinite, and Orthopyroxenite, depending upon which portion of moon they were coming from, what kind of source, how deep that was coming from. Then we also have some rocks from moon. They are called lunar meteorites. We have some meteorites from asteroidal belt. They are called Howardite, Eucharite, and Diogenites. So they come from Vesta and Pallas, some of the large objects that we see in the asteroidal belt and that we talked about in the very first lecture. But the major discussion that we'll be making would be about chondrites. Chondrites are primitive bodies that have not gone through any kinds of melting or differentiation. So they are classified into three types called carbonaceous, ordinary, and encephite, depending upon what kind of bulk elemental composition they have. They are further subclassified into different types depending on how much different components of these are incorporated into each one of them. So, for example, carbonaceous chondrite is classified into carbonaceous type of Evuana, which is called CI in short, or carbonaceous chondrite of Murchison type, CM type. Similarly, CV, CH, COR. So C for carbonaceous and then IMO for the representative sample of that particular group. In ordinary type, we have three types with different amount of abundance of iron. So if it's a high abundance, it is called H type. If it is low abundance, then we have low L type, and if it is very, very low, then it's called LN type. So this is broadly about the classification of meteorites. We'll be primarily talking about chondrites, which have got chondrules. So a typical chondrite looks something like this. This is a cut. This is a sliced, polished section of a chondrite, and what we see here, over here is a backscattered electron image of the meteorite. So in this, what you can see that there are several spherical balls. There are several spherical igneous balls. Some of them have been deformed into different shapes. These spherical igneous balls are called chondrules. Then there are other objects like these, irregular shaped inclusions between these. We will see in the following slide immediately. They are called CAIs, and there are other kinds of objects called amoeboid olivine aggregates because they are shaped they have an irregular shape like an amoeba. They are primarily constituted by olivine, and they seem to be an aggregate of things, and therefore they are called as amoeboid olivine aggregate. Typically, a meteorite is named after the place it falls at. So it would get the name of the place where it falls, and then you would see something like this, which would be its classification. So if it is a carbonaceous chondrite, so it would have C. If it is of Renato type, it would have R. Then its petrologic type, which would say how much transformation or alteration this object has seen since its formation. So the best preserved samples belong to category 3.0. So this is one of the meteorites that fell in Antarctica in year 1999, and it was the 177th sample that was collected by NASA Antarctic mission in the year 1999 at the area called Queen Hills. You can see the scale. 1 millimeter is at this level. So if these objects have there is a diversity in the distribution of elements between these objects. So if you make a X-ray maps of these objects and you combine them together, then these different objects immediately pop out. So this is a combined magnesium, calcium, aluminum map of the same object that I showed in the previous slide. The abundance of magnesium is shown by red. The abundance of calcium is shown by green, and the abundance of aluminum is shown by blue color. So an object which is rich in calcium and aluminium would appear greenish blue, and therefore it is very easy to figure out that this is a CAI, which was not so clearly visible in the previous slide. Similarly, this diversity is very clearly popped out by having the X-ray abundances. So you can see this is an aluminum-rich chondrule. You have a lot of blue over here. This object is rich in alumina, and there is an amoeboid olivine aggregate over here, which is primarily olivine, means it has magnesium, and then so that's how we. So there are other refractory objects like over here. You can see over here, and there are small objects, very small objects over here. So a chondritic meteorite typically consists of chondrules, as I said, then refractory inclusions, and then amoeboid olivine aggregates, and all of these is cemented together by a very fine dust, which is called as matrix. Of course, there are iron, metal, and sulfides of metals in the surrounding area. So if we enlarge that image of CI, this is how it would look like. We will look at these in more details. So as I said, meteorites, chondrites are of different types, and the different types of chondrites appear differently. So you can see this is an ordinary chondrite. So this is primarily these are the most of the spherical balls, while these have got different kinds of objects. They are not at the same scale. This is about 3 times more enlarged image of this than this one. So if you compare at the same scale, this is how it would look like. So yeah, so this is how it would look like. So now you can see that most of these chondrules, these spherical balls over there, they are pretty much bigger. They are much bigger than the objects in this kind of a meteorite, which is a carbonaceous meteorite. So the abundance of different components, CIs, chondrules, and metrics, the model sizes of these objects, CIs, chondrules, the mineral composition of each one of them are distinguishing feature and characteristics specific of each particular chondrite. For comparison, we are going to see the magnesium map of these elements. So we can see that because this is a CI, this has got very low abundance of magnesium, while chondrules have a larger abundance of magnesium, and therefore most of these objects are chondrules, and we can very easily see over here, which is more, we can clearly identify these objects and see what kind of objects these are. So this slide shows you the combined bulk, the combined magnesium, calcium, and aluminum map, where the abundance of magnesium is shown in red, abundance of calcium is shown in blue, and abundance of calcium is shown in green, and abundance of aluminum is shown in blue. So an object like calcium aluminum inclusion, which would be rich in calcium and magnesium, would appear something like grayish blue, something like that over here, here, and here. And you can see that their abundance varies between different objects. So while these are pretty large in type B CIs, a representative is over here, is much bigger in a carbonaceous chondrite of Vigrano type. These CIs are smaller, or they are more fine-grained in carbonaceous chondrite of Reynolds type. Similarly, you can compare the sizes of the chondrules and the amount of matrix in each one of them. So large diversity in the meteorite exists in these kinds of objects. Chondrules also come in different types. They can be differentiated from their morphology. So some of them have very large crystals, or porphyries as they are called. These chondrules are called porphyritic chondrules, while there could be some which have got very small grains. They are called fine-grained or cryptocrystalline chondrules. Then, depending upon their abundance of magnesium and iron in them, they are classified into type 1 and type 2. Type 2 being rich in iron. So, if the iron abundance is greater than 10%, then it is called type 2. If it is less than 10%, it is called type 1. There are some chondrules which are rich in aluminium. They are called as aluminium-rich chondrules. So chondrules are another major constituent of the meteoroids. They are igneous spherical balls, typically a few centimeters in size. They are primarily made up of iron, magnesium, olivine, and pyroxene. They have a lot of iron, nickel, metal, and sulfides, and a lot of glass as a matrix in between. So the other kinds of meteorites like chondrites and primitive are shown in this particular slide. They are iron meteorites. So the silicate inclusions in those meteorites are shown in transmitted light with cross polar. So there are olivines like over here, and then there are pyroxenes over here. They are surrounded by the iron. So the silicate within the iron meteorites in bionite and iron meteorite are shown in this particular figure as an illustrative example of what kind of difference we see between the chondrites and between the iron meteorites. So as I said initially, because of the different amount of uh, these three different components, their bulk composition varies in the amount, in the abundance of different elements. These have been plotted in the decreasing order of their melting point. Uh, therefore, the varying amount of refractory component that would be constituted by different groups of meteorites, they would follow different patterns, and they can be easily classified or differentiated based on the abundance of these elements compared to a standard CI type, which is similar to the composition of our solar system. So similarly, that can be done for metals, osmium, iridium, ruthenium, nickel, and each different chondrite type show a different pattern. Isotopically also, because these refractory components contain uh, they inherit different amount of these components which have very distinct signatures that we'll see in the next lecture tomorrow, and therefore their isotopic composition, the bulk isotopic composition is also different, and they fall on two different trend lines. So Earth Moon lies over here, while COCB chondrite lies, the carbonaceous chondrite lies on this kind of a trend, while the non-carbonaceous lie on this particular trend. The similar kind of a trend is also seen in the oxygen and chromium isotopes of these meteorites. So that's how these meteorites can be classified. Oxygen is one of the is a major characterizing characteristics of these objects, and they lie different on different areas on this 3 oxygen plot, as it is called. So delta 17O is plotted against delta 18O with respect to with reference to our solar system, and these different groups of chondrites lie at different places. They have been shown by different symbols. So a triangle shows CR type, a hexagon, filled hexagon shows CM type. So now to the specific question that we were talking about. So we just can't take the whole reason for saying so much about the chondrites and uh, was that if we really want to look for a particular signature, we just can't randomly go and take a meteorite and do something. We have to be very specific, and we have to be very judicious in choosing a particular meteorite to look for a particular signature. So now, if you want to look for a signature of whether the collapse of our molecular cloud was triggered or not, we are going to look for a nuclide 60Rn. We are going to look for a nuclide 60Rn because 60Rn is primarily produced only by stellar nucleosynthesis, uh, and the amount that is produced by different stellar sources like AGB or supernova or WR star is different because of the different amount, the different mechanism operating to generate 60 Rn. So by finding out the abundance of 60 Rn in the meteorite, we can say what source contributed to it, or there was no source contributed. We had just the ambient material from the interstellar medium. So supposingly an object incorporated 60 Rn at the time of its formation, then 60 Rn over a period of time would decay into 60 nickel with a characteristic half-life of 2.62 million years. Then we can form a linear relationship of similar type by dividing with a stable isotope of nickel isotope which doesn't have a radiogenic precursor. So we'll get a relationship like 60 nickel by 61 nickel or 62 nickel. Then the slope of this line would give you the initial 60 by 56 Rn that was present, and then we can find that in a few objects. So because if you remember, in the previous slide I said that chondrules comes in two different types, type 1 and type 2. Type 1 have got low iron, less than 10%, while type 2 have got high iron. Since we are going to look for a signature of 60 iron, which is an isotope of iron, we are going to look for type 2 chondrules, and then do several more studies to be able to figure out what suitable sample. So from more than 250 chondrules, we selected about 50 chondrules which had the potential to be analyzed both for 26 aluminum and 60 iron, and then we analyzed those 50 chondrules for both aluminum and magnesium. In this plot, we show those 7 chondrules, except for this one, which gave us result both for aluminum as well as for iron. So the aluminum analysis were conducted at regions shown in green, while iron analysis were carried out at circles shown in red. So aluminum is found primarily inside the glass. So the in-between region mesostasis was analyzed for aluminum magnesium, while iron is primarily found in olivine and pyroxene. So olivine and pyroxene, which is more brighter in these figures, were analyzed. So by analyzing we analyzed about 50 of them. These 7 of them gave us result both for 60 iron and 26 aluminum. Could give us a clear-cut resolved excess in 60 iron, and so 4 of them are shown. For example, Semerkona chondrule 3 gave us that the initial abundance at the time of formation of this chondrule was 3.2 times 10 to power minus 7. The intercept was 0.0 plus minus 2.2. Similarly, for a chondrule like from Lewis Hill 86134, which is an Antarctic meteorite from the expedition in 1986 in the area Lewis Hill, we obtained that it had initial 60 iron 4.2 times 10 to the power minus 7, which is slightly higher than 3.2 that we see over here. And in Semerkona chondrule 18, this is almost double that same amount. So in Semerkona chondrule number 18, we see that the abundance of 60 iron by 56 iron is 7.4 times 10 to the power minus 7, which is double the amounts of these two chondrules. So two chondrules are forming at different times, and therefore, if you remember what I said initially in the while showing as to how these isotopes would decay and give different amounts of slope. So these slopes are shallower compared to this particular slope. Expectedly, this chondrule formed earlier and therefore incorporated larger amount of 60 iron compared to the chondrules which formed later in time. So by analyzing these 7 objects, which show a range of 60 iron by 20, which shows a range of 60 iron by 60 iron by 56 iron, we could find both the abundance of 60 iron and 26 aluminum in these objects. So we could find that these objects have got varying abundance of 26 aluminum by 27 aluminum, and they also have varying abundance of 60 iron by 56 iron. So as I said initially, we know the starting canonical abundance of these of 26 aluminum by 27 aluminum, which is equal to 5.2 times 10 to the power minus 5. So we can calculate from that canonical number 5.25 times 10 to the power minus 5. So in one half-life, it would reduce to 2.5 times. So that means that chondrule like this would have formed about one half-life of 26 aluminum, which is about 0.73. So you can use that relation to find out at what time these chondrules were formed from their 26 aluminum abundance. And then we can use this time to find out what was the abundance, what is the inferred abundance of 60 iron at the time of the formation of solar system, at the beginning of the solar system. So what we can see is that from different chondrules we get slightly different numbers. We can average out all of them, and we find that the value that would correspond, that would explain, that would be compatible with most of the values that we get is about 7.0 plus minus 1.2 times 10 to the power minus 7. So if the solar system was initially seeded by this much amount of 7 times 10 to the power minus 7 times of 60 iron by 56 iron, then different chondrules forming at different time would incorporate different amount of 60 iron which we see today, and thereby we can establish that this much of 60 iron should have been seeded at the time of the formation of the solar system. So then, since once we know the amount that was seeded into the solar system, then we can look at the nucleosynthetic models, nucleosynthetic yields from the stellar evolution, and then we can calculate if there is a scenario by which the amount of material injected by a supernova or a surrounding star can explain not only the abundance of 60 iron but the other radionuclides that we showed in the chart. So we have selected 4, 5, some of the shortest radionuclides with shorter half-life, less than 9 million years in their life, and then we can compute it for different stellar masses. The yield from different stellar masses can be used to find what kind of material should be injected into solar system to be able to explain the abundance that we have inferred for the solar system. So for a nucleosynthetic yield from models by Goosley and their co-workers that was published in Rauscher et al. In 2002, we can see that that we need different amount of material, different level of material from different times from these stars to be able to explain the observed abundances. So this is plotted. So let me go back to the next slide where I've shown up. So this is the injection value versus the meteoritical value. So the observed value is 1 for different where we have normalized all of them to the value that we see, and then we have used the material as to how much of material from the core of the star. If all the material from core of the star were mixed with the solar system, then these plots would go over there. If the outer material outside 2 solar mass of the star were to be mixed, then this would be the curve. Similarly, so what we find is that if we mix from a 25 solar mass, if we mix the material from the outer 7.8 mass of this 25 solar mass star, then simultaneously we can explain the abundance of abundance of 60 Rn, 182 hafnium, palladium, and 26 aluminum. So that's how by computing these for another model by Limongi and Jeffrey, we could find more or less the same value for different stars. For 25 solar mass, we need material from 6 solar mass injection mass cut, while for a more massive star, which will give because of their more mass, it will generate more amount of 60 Rn. We need less of a mass from. So we need material outside the 8 solar mass. So that's how we could find out not just. So by computing the abundance of 60 Rn, we could go back and use the nucleosynthetic yield from the stellar sources to compute what amount of material should have been injected at what particular time to be able to explain what we see now in this solar system. So this plot shows what all 60 Rn versus 56 abundance is known in different objects. So these are CIs. The ones shown in yellows are the observed abundance that we see in CIs. Then the abundance that is seen in different chondrules inside the trolite minerals inside around the chondrules, and then in the differentiated objects in measured by bulk multi-collector inductively coupled plasma mass spectrometry. So you can see a lot of range is seen in different objects, which is expected, but the difference is pretty large. So what we see with the bulk measurements, in this slide we show all the objects that have been measured by SIMS, all the objects that show a higher value in terms of CIs as well as in chondrules and sulfides. The value that would explain all of them is somewhere around here, 7 times 10 to the power minus 7. These objects form at a different time and within error. And if you account for their time of formation, this value would be compatible with what we see in those objects, in these objects. But if you go and look at the bulk measurements that for the differentiated and differentiated objects, as well as for some of the bulk measurements of the control, they don't seem to be compatible. All the differentiated objects tends to show a value very close to 1 times 10 to the power minus 8, which is about 60 times less than what we see from the in situ measurements in the chondrules that were done. So you may not have noted, but in the previous studies we just measured 2 isotopes of nickel. That means we measured just 60 and 62 nickel because of the analytical precision issue with the older generation ion microprobe. So we did not correct for the instrumental mass fractionation. We did not correct for the possibility of the mass fractionation that could exist during the formation of these objects. So another set of experiments were carried out, and those measurements were made with the latest state-of-the-art machine, and which allowed us to measure all the 3 isotopes, so that we could make corrections for the potential mass fractionation issues. So these measurements were carried out for 2 chondrules from Semerkona and 1 chondrule from Ifrimuka, and similar to the previous studies, we again saw a similar range of similar varying range of abundance of 60 Rn inferred by different slopes of these lines, which could be explained, which was compatible to the previous studies. So the other issue that we wanted to settle out is whether they were injected simultaneously or they could be emanated by different sources, and therefore they could have come decoupled. So by combining the study of both aluminum and iron, where the abundance of aluminum in these objects is plotted on x-axis, with respect to the 60 Rn abundance seen in those same objects with respect in those same objects. If both these were injected simultaneously, then those objects forming after the time of homogenization would show a uniform trend. If 26 aluminum and 60 iron were decoupled or were injected at different times, then possibly, because let's say if the 60 iron was injected at this particular 1 million year after the formation of solar system, then these objects, because iron was injected over here and these objects formed prior to that injection, then they should have shown a very low value of 60 iron. So since we could find objects which form right at almost at the time of the formation of the solar system, we could infer that both 26 iron and 26 aluminum and 60 iron should have come from a same source, and these objects formed in a homogenized. To be able to follow this particular trend where all these objects seems to be falling on a same line, it should have been from a same source and be derived from a same homogeneous environment. By calculating as we calculated as I previously showed, these are all compatible with the value of 7 times 10 to the power minus 7 abundance of 60 Rn by 26 Rn, with the canonical 5.2 times 10 to the power minus 5 for that of 26 aluminum. So I've said most of these conclusions that by determining the abundance, we could determine the abundance, which we found out to be 7 times 10 to the power minus 7. We could also show by using the modeling that these could be derived from a high mass supernova of about 25 solar mass, and they should have been co-injected to be able to explain the correlation that we see between the 26 aluminum by 27 aluminum and 60 iron by 56 iron in those objects. But the bulk measurements carried out recently, very recently, show a slightly different picture. If you make the bulk measurements in some of the Samarkand chondrules, Nicholas Dofas obtained a value which is about 60 times lower than what we see in the in situ measurements. Some of these can be explained because we are looking in situ measurements, we are looking specifically at the phases which host very high iron by nickel ratios. So if for some reason the chondrule had some contamination, or while during the separation or during the there was some then the iron nickel which is not host into that chondrule could alter or reduce or by the amount, and therefore slightly shallower slope could be received. So if the in situ measurements are to be believed, all these chondrules should have lied on this particular line, but the two chondrules that were analyzed by Tang and Dofas, they showed a value which is 60 or 70 times lower than in the differentiated meteorites. They obtained a value which is 1 times 10 to the power 9. These two measurements seems to be compatible, but they are not compatible with the in situ measurements that were carried out by the studies that we carried out. One of the chondrule from Samarkand, which did not show a resolvable 60 Rn by 56 Rn, was analyzed with another advanced technique called resonance ionization mass spectrometer, which takes care of several analytical issues that could be with the SIMS or MCIC previous studies. From this, they infer that solar system was seeded with a much lesser amount of 60 iron, but for me it's difficult to say because this chondrule did not show a resolved excess in either of the measurements. So showing a zero value for showing a chondrule with a 60 iron was measured by the in situ measurements to be equivalent to the zero value measured by the RIMS measurement is to my mind is not a strong enough argument to show that the abundance of 60 iron was low in the early solar system. So although we have shown So although our studies showed that there exists a higher abundance of 60 iron by 26 iron, the bulk isotopic measurements carried out by MCIC PMS on the bulk chondrules as well as on mineral separates show a value 60 or 70 times lower than 60 iron, which would still be explained by a stellar source, but not the supernova as we claim in our as we have inferred. So there still exists that discrepancy between what kind of a stellar source contributed to it. If results of our in situ measurements were to be believed, then the contributions would have come from supernova. Therefore, the formation of our, so if a supernova happens very close to our solar system, then it would be a very triggered collapse. If it happens by another stellar source like WR Wolf-Rayet star or an asymptotic giant giant star of a higher massive star, there would the wind of that collapse would have a gentler impact on the collapse of our molecular cloud, and then would have a slightly lesser amount of seeding and those kinds of issues. So with that, I will stop. I've come to the end of this particular uh, talk. I acknowledge some of the material that were used from books and research papers and website, and I'm grateful to all the authors and contributors of this useful material and information. With this, I will welcome any suggestion, comments that you might have, and I'm happy to answer any question that you might have.